This screencast is going to focus on finding the simplest empirical formula for different compounds. And typically you're given percent composition data, and then you move from there. And so if we think about what an empirical formula means, just the word empirical typically means that there's proof behind it. So there's some sort of experimental evidence that you've been given. So kind of a classic lab is you take a compound and you break it down into the elements that it contains, and then that's how you can get a percent composition by mass. But we know that just because we know the masses of objects, that doesn't necessarily mean the ratio of one element to another element is going to be the same with mass. But what we can use is moles. So you'll see in a little bit when we're finding these simplest empirical formulas, typically the first step is always going to be to get them into moles, because we can compare a mole to mole ratio. We just can't compare a mass to mass ratio. Now if we back up a little bit, when we've been naming compounds, we've seen things like this pop up, P4O10. This would be, as you guys know, when two nonmetals get together, this would be a covalent compound. Now, when we did ionic compounds, we never saw ratios like this. Like we wouldn't see Na4O2, even though that reduces to Na2O, right? This is an ionic compound, and when we write the chemical formula for ionic compounds, we always write them in the simplest whole number ratios. And the reason is because if you think back to that model that we have of a crystal lattice, we know that in an ionic compound, it's this big array or lattice work of positive and negative ions. So when we write a chemical formula for an ionic compound, we're showing what the ratio is between the cations and the anions. So even though this ratio is still maintained, it's still a 2-to-1. Ionic compounds, when we write their formulas, are in the simplest whole number ratios. But for a covalent compound, we know that electrons are being shared, and sometimes it takes more than a simplified ratio in order to get enough electrons for their octet. Whereas in an ionic compound, we're talking electron transfer so that the nonmetal can get its octet by taking electrons from the metal. So this would be perfectly fine for a covalent compound, but we wouldn't ever want to write an ionic chemical formula like that. So if you think about the definition of empirical formula here, it says this, a compound expresses the simplest whole number ratio of elements in that compound. Okay, well for an ionic compound, its empirical formula is always going to be its true formula. So that applies to ionic compounds. Okay? But if we look at this, if this was the real formula for our compound, we know that mathematically that could simplify to P2O5. And you can't get any simpler than this. So this would be considered the empirical formula for P4O10. So the empirical would be diphosphorus pentoxide, and the molecular formula is what we're going to call this, is tetraphosphorus decoxide. And so in our next lesson, we'll move from empirical to molecular, but today we're just going to focus on, well, how do we get these empirical formulas? So I've put the steps in your notes, and I've also come up with this little jingle. And actually, I don't know if I came up with this jingle or if somebody else did. So sorry if I'm not giving credit to the teacher who came up with it. And so it's not really a rhyme, because it doesn't rhyme, as students have pointed out to me, so I've stopped calling it a rhyme. But it's kind of a jingle. And it kind of helps you remember these steps, okay? So the first step is to change the percent grams to moles. Well, that's going to be pretty straightforward. We've got 75% carbon in our first example, and so I'm just going to change that to 75 grams of carbon. And I'm going to start my bridge. And then my 25% hydrogen, I'm going to change to 25 grams of hydrogen. So just by doing that, I've done my first step. So the little part of that is percent to mass. So we just took off those percents and changed them to grams. All right, so then they want you to find the mole ratios. Oh, sorry, we haven't done this yet. The grams are going to have to be changed to moles. So you guys know that this is just going to be a one-step conversion to go between grams and moles. So the molar mass for carbon is 12. So when we do that, we get 6.25 moles. And then when we do the molar mass for hydrogen, and guys, we take all of our molar masses to 1 decimal place. For hydrogen, I would make a note that it's probably better to take this to 2 decimal places. And it's not something I'm going to take off for, but you do get nicer numbers, and I'll show you what I mean by nice in a minute. Okay, so we've done percent to mass and mass to moles. All right, so now it says find the mole ratios by dividing by the smaller number. Okay, so when I look at this, right, this is by mass. So obviously when we look at this, we've got more mass of carbon than we do of hydrogen. But look at what happens when we get it into moles. We've got a 6 1/4 to 25 ratio of moles between the two. And what we're going to do to simplify that, because obviously we've never seen, subscripts like 6.25, we're going to divide by the smallest to see what the whole number ratio is. So clearly there we get 1, and this will go into 25 4 times. So what you get right there are these nice whole numbers. And so it says if whole number ratios are not obtained, then we're going to have to multiply. But clearly we get nice numbers here. So then those numbers become the numbers associated with that element. So this was for carbon. So that means we have 1 carbon, and we don't write the 1, right? It's understood. And then we have 4 hydrogens. So your empirical formula is CH4. Okay? So percent to mass, mass to mole, divide by small, and that last step, multiply to a whole, we didn't have to do it here because it was nice, clean whole numbers. And I'll show you what we do when that is not the case. Alright, so number 2 kind of works the exact same way between potassium and chlorine. Now this is one where you could probably predict what the formula will be, because this is an ionic compound, and so you should get KCl when you do that one. Now sometimes students will be like, well, can't we just say it's KCl? If you're writing a formula, that's totally fine. If they're giving you percent composition data, then I expect you to work it out. So you may want to pause the screencast right now and see if you can follow those same steps to get KCl. We're going to do this next one together just because it has 3 elements, and sometimes that stresses students out, but it clearly works the same way. So we're going to take 22.1 grams of aluminum, start our bridge, 25.4 grams of phosphorus, do our bridge, and 52.5 grams of oxygen. Alright, so now we're going to get all those grams into moles. And so I take those molar masses from the periodic table. You guys are experts on that by now. Alright, so 27 grams per mole of aluminum, 31.0, it's 30.97 on the periodic table, but that 7 kicks it up. And then oxygen is 16.0. Alright, so we get all of our moles. We get 0.819 moles for aluminum. We get 0.819 moles for phosphorus. And we get 3.28 moles of oxygen. Okay, so percent to mass, mass to mole. Now we're going to divide by small. So I'm going to divide this by 0.819. We get 1. Divide this by 0.819. We get 1. Divide this by 0.819. And we get 4. Again, these are all nice whole numbers. We'll see in a minute where that doesn't happen. And so these become our subscripts. So we've got 1 aluminum, 1 phosphorus, and 4 oxygens. So our chemical formula is AlPO4. This is ionic. You can't really predict it from this because you don't know, is it phosphate or phosphite? In this case, it's aluminum phosphate. But you can certainly check your work because I won't make any wrong ionic formulas. And so when those two get together, they do make AlPO4. So for every 1 aluminum ion, you have 1 phosphate ion in your crystal lattice. Okay, so the general rule that we use, whether or not you can round this, because when you calculate this, this may come out to be like, 4.01. Well, is that okay to round to a whole number? The rule that I use is if you're within 0.05 of a whole number, then you're welcome to round it. Now I say that, and students are like, well, what do you mean by 0.05? Well, if you add 0.05 to this number, right, it's still within a whole, pretty close to being a whole number. If you got something like 4.5, you can't round that and say that it's 5 or say that it's 4. So that's when you have to do the last little part of the jingle, which is multiply till whole. So we're going to see that with this one, with aluminum and oxygen. Now, they start you out with grams, and sometimes students will like get the total mass and put the mass of aluminum over the total times 100. You don't have to do that, guys. They're telling you that in a lab, they recovered this much aluminum and this much oxygen. So just basically what they've done is the first step's done for you. You don't have to do percent. So we'll start with our 4.151 grams of aluminum, and on the bottom we'll have our 3.692 grams of oxygen. Okay, so we're going to get our grams into moles, just like we've been doing. So 27.0, 16.0. Alright, so for aluminum we get 0.154 moles. We're limited to 3 sig figs because of that. And then we get 0.231 moles of oxygen, limited to 3 sig figs because we cut those off. Alright, so we've got our mass to moles. Now we're going to divide by small. So the smallest one between these two is the 0.154. So I get 1 there. That's a nice number. But here I get 1.5, and there may be another digit there. But I get 1.5. So guys, you can't have 1 and 1.5 atoms getting together. It just doesn't work that way. But we do want to maintain that ratio. And so if you think about 0.5 and turn it into a fraction, I know you guys may not like fractions, but they're going to be pretty basic fractions. So that's like a half. So for every 1 atom of aluminum, we need 1.5 of oxygen. Well, we can't have that fraction. So what you do is you multiply by a number that will clear that fraction. And so if you think about a half, if I multiply that by 2, then you guys know that that cancels, right? And you end up with 1. So here, when I multiply 1.5 by 2, I'm going to get 3, and here I get 2. So now this ratio, this 2 to 3 ratio, it's the same ratio as a 1 to 1.5, but it's in whole numbers, which is what we need for chemical formulas. So Al, the subscript is going to be 2, and for oxygen, the subscript is going to be 3. Okay? So that's what that last step means. The most common, if you want to make a list of, for this last part, if it's not whole, so I'll show you the most common. So if you end up with around 0.5, so again, that could be 0.48 or 0.51, then I would multiply by 2, and that'll clear it. If you get something close to 0.25, so that's like a quarter, right? So if we want to clear a quarter, we would multiply it by 4. If you get 0.33 or 0.67, then the best thing to multiply by is 3, because that's like a third, 1/3, and this is 2/3. So by multiplying by 3, you'll clear those out. So these by far are the most common. So that's why I just put multiply by 2 or 3. And you know, if this does not make sense to you, in your calculator, just sit there and try it. Multiply by 2. See if you get closer to a whole number. Multiply by 3. See if you get closer to a whole number. Just remember that whatever you do to one, you have to do to all the atoms in that compound. So just like in math, whatever you do to the left-hand side, you have to do to the right-hand side. So make sure you're multiplying through by that whole number, okay? And when you multiply, the 0.05 rule still applies. So if you end up with a whole number that's like 3.04, that is okay to round it to 3, okay? So just think of like being a nickel within a dollar. So that is a nickel within a dollar. So that would be fine to round. Now when you get to the backside, so you're going to do the backside for practice. The first 4 are very similar. I will tell you a sig fig note on this one. You end up with, I forget what the exact number is. Let me see if I've got it here. Okay, so you end up with 0.00697 blah, blah, blah from your calculator. And what I see a lot of students do is round this to 0.007. And guys, here you have 4 sig figs, here you have 4 sig figs. If you do this, you now only have 1 sig fig. And so it's really important that you watch, because these zeros are not significant, okay? So you've cut this to 1 sig fig, and that will definitely mess up your ratios when you get finished. All right, so do the extra practice, and then we will check those together.